Hello everyone, my name is Shubham Gill and today we are going to discuss about magnetic field due to current carrying conductor. Now this presentation is meant for class 10th CBSE students only. So in this presentation we are going to be talking about what are magnets, magnetic field due to current carrying conductor, right hand thumb rule, magnetic field due to current in a circular loop, magnetic field due to current in a solenoid, electromagnets, force on a current carrying conductor in a magnetic field. Similarly, corresponding to it is Fleming's left hand rule, electromagnetic induction, DC and AC currents, domestic circuit, and electrical fuse. So, what are magnets? A substance which attracts small pieces of iron and points in the north-south direction when suspended freely is known as a magnet. A naturally occurring iron ore, which is also called lodestone or magnetite, also behaves as a magnet, but it is a very weak magnet. Magnetism in natural magnets is often lost over time. So what we need is a permanent magnet and also a strong one. Therefore, we require artificial means to prepare them. Now, what are the properties of a magnet? Well, it has two poles, north and south, and another property of a magnet is that it repels like poles. That means north repels north and south repels south. So, and unlike poles, that is north and south, they attract each other. We cannot have a magnetic monopole in isolation. That is, we always have a dipole. By dipole, I mean north and south. So, even if you cut a magnet, both the pieces of a magnet will start behaving as individual magnets with north and south pole. Repulsion is the only sure test for a magnet. Why is that? That is because magnet attracts iron, also attracts another like pole of a magnet. Therefore, you cannot be sure if the other substance is a magnet or is it just another piece of iron. Now, a magnet is identified with its magnetic field and magnetic field lines. So the question comes, what is a magnetic field? The region around the magnet where an object placed will experience a force of attraction or repulsion from the magnet is called a magnetic field. As shown in the figure, we have a compass whenever it's placed in the close vicinity of a bar magnet shows deflections. The deflection are caused by the attraction and repulsion from the magnet. Why this happens is because the compass needle is magnetic in nature. It is just another bar magnet. Therefore, it's going to experience the force of repulsion or attraction whenever it's placed near another magnet. A magnetic field is characterized by its magnetic field lines. These are paths around a magnet along which the north pole of a magnetic compass needle tends to move. The magnetic field lines around a magnet can be observed by sprinkling a few iron fillings around a magnet. It can also be shown by moving a magnetic compass around the magnet. As shown in the figure, you can see these magnetic field lines originate from the north pole of a magnet and terminate at the south pole. So, the following are the properties of a magnetic field line. They emerge, like the first one is pretty clear, they start from the north pole and finish at the south pole. Magnetic fields are closer at the poles, indicating a very strong magnetic field at the poles. These lines never intersect each other. What happens if they did? Because if they did, that would show that a magnetic field has two distinct directions at the same point, which is practically not possible. Therefore, they never intersect each other. Magnetic field due to a current carrying conductor. If a magnetic compass is placed near a conductor carrying current, which can be a wire, the needle will show deflection. This shows that a current carrying conductor has a magnetic field around it and it exerts the force on the compass needle. For example, as shown in the figure below, if the direction of the current is from north to south, you can see that the deflection of the magnetic needle is towards the east. And if the direction of the current is from south pole to the north pole, you can see that the needle is deflected towards the west. The magnetic field around a current carrying straight conductor is in concentric circles. and it can be observed by passing a current carrying straight conductor through a cardboard and by sprinkling iron fillings on it or using a magnetic compass. To know the direction of the magnetic field around a conductor, we have Maxwell's right-hand thumb rule. Now, it states that if a current carrying conductor is held in the right hand such that the thumb points in the direction of the current, then the fingers wrapped around the conductor shows the direction of the magnetic field, as shown in the figure. Magnetic field due to current in a circular loop. We just saw the magnetic field direction in a straight current carrying conductor. What if we convert that shape into a circular loop? As shown in the figure, when a current is passed through a circular conductor or a loop, the magnetic field produced is in form of concentric circles around the same conductor. Towards the center, the arcs of the circle become larger and appear as a straight line. As you can see over here in this figure, you can imagine this conductor being a straight current carrying conductor, and we use the Maxwell's right hand rule to identify these concentric circles, and the direction now as shown by the direction of our fingers can be seen over here. As we move away from this center towards the center of the as we move towards the center of the loop, we can see the circles become larger and become almost like a straight line. Magnetic field due to current in a solenoid. A solenoid is a circular coil of wire in the form of a cylinder. Whenever a current flows through the solenoid, it behaves like a bar magnet. The ends of the solenoid behave like the north and south poles of a magnet. The magnetic field produced by a solenoid is similar to the magnetic field produced by a bar magnet. The strength of the magnetic field depends upon the strength of the current and the number of the turns in a coil. Now this is shown in the figure here. Now, as shown here in the first figure, we have a battery which is connected to the wires being wound up on the solenoid. Like it said, the magnetic field B is directly proportional to the number of turns N and the amount of current flowing through those wires I. Mu is the constant of magnetism. Now, as you can see, if we plot the direction of the magnetic field of this solenoid, we get the figure 3, which is quite similar to the magnetic field lines drawn for a bar magnet. A strong magnetic field inside a solenoid can be used to magnetize a piece of magnetic material like soft iron core when placed inside the coil. Such a magnet is called an electromagnet. The magnetism exists because of electricity flowing through it in form of electric current. Now, as you can see in the figures below, if electric current is passed through the wire and wound around a piece of soft iron core, that material now behaves like a magnet. As you can see, we have an iron nail on which we have wound our copper wire, and which is connected to an electrical circuit. Now, if we see the direction of current as represented by the fingers in the Maxwell's right hand rule, we can find out the direction of the north pole and the south pole, which will be given by our thumb. That is, our thumb will point in the direction of north pole. Force on a conductor carrying current in magnetic field. Ampere suggested that if a current carrying conductor produces a magnetic field and exerts a force on the magnet, then a magnet should also exert a force on the current carrying conductor, in accordance with the Newton's third law. So we did an experiment where, say, an aluminum rod is suspended horizontally between a wire and the poles of a horseshoe magnet, and current is passed through the wire, then the aluminum rod is displaced. However, if the direction of the current is reversed, then the direction of displacement is also reversed. This proves that the force exerted is maximum if the conductor is perpendicular to the magnetic field. And the force exerted also depends upon the direction of current in the current carrying conductor. Fleming's left hand rule. The direction of force that is the motion of a current carrying conductor placed in a magnetic field, is given by Fleming's left-hand rule. If we hold the thumb, forefinger and the middle finger of the left hand perpendicular to each other such that the forefinger points in the direction of magnetic field, the middle finger points in the direction of current, then the thumb shows the direction of force or the motion of the conductor, as shown in the figure below. Electromagnetic induction given by Michael Faraday. The motion of the magnet with respect to a coil or a change in magnetic field will induce a potential difference or an EMF in the coil, and which in turn produces induced current. This is called electromagnetic induction. Now please note that we mean motion of the magnet, that is continuously changing magnetic field with respect to time. Now as long as the magnet is moving, there is a continuous motion of the magnet with respect to the coil. Current will be there in the coil. Whenever the magnet is stopped, current stops flowing. As given in the figure, if a magnet is moved towards or away from the coil of a wire connected to a galvanometer, the galvanometer needle shows deflection. This shows the current is induced. You can see here that when the north pole is inserted inside the coil, galvanometer shows a deflection towards the left. However, if this same magnet is taken outside, then the galvanometer shows the deflection in the opposite direction, showing the direction of the current has now reversed. As discussed earlier, change in magnetic field produces induced current. Take two coils of wires wound around a cylindrical paper roll. Connect one coil to a battery and the other coil to a galvanometer. If the current is passed through the first coil, the galvanometer shows a deflection in the second coil. However, if the current is disconnected, the needle moves in the opposite direction. This shows that the current is induced due to change in magnetic field. To know the direction of induced current, we use Fleming's right-hand rule. It states that if the thumb, forefinger and middle finger of the right hand is held perpendicular to each other such that the thumb points in the direction of motion of the conductor, forefinger is pointed in the direction of magnetic field, then the middle finger shows the direction of induced current. Direct and alternating current. Direct current, or commonly known as DC, is the current that always flows in one direction. This current does not change with time. The current we get from the battery of a cell is a direct current. Alternating current, or commonly known as AC, is the current that reverses its direction periodically, and that thus is called alternating current. Most power stations in the country, our household supply, everything is AC, that is alternating current. The advantage of AC current over DC is that it can be transmitted over long distances without much loss of energy using transformers. Domestic electrical circuit. Electrical power to our household is supplied through mains. It has two wires. One is the live wire, that is the positive wire, which is red insulation, while the other is the neutral wire, the black wire, and it is also known as the negative wire with black insulation. The potential difference between the two wires is always 220 volts. The earth wire with green insulation is connected to a metal plate kept on the ground. Two separate circuits are used. One is of 15 ampere for appliances with high power ratings such as geysers, air conditioners, etc., while the other is for 5 ampere, which uses fans and bulbs, etc. The different appliances are connected in parallel so that every appliance get an equal potential difference, that is what we call voltage, and even if one of them is switched off, the others are not affected. So for example, all the appliances, take your example of a fridge. So if your fridge is turned off, it doesn't mean that your entire household supply and all your lights, your TV, your air conditioner, they will get turned off also. It doesn't happen that way. That shows that every appliance is connected in parallel. The appliances having metallic body like electrical iron, refrigerators, as mentioned earlier, They are connected to the earth wire. That is the third wire, which is also sometimes known as the green wire, is there to prevent any leakage of current which will give us shock once we touch their metallic body. So in order to prevent that, we have the earthing wire connected to the metallic body. An electric fuse. Now, electric fuse is a safety device in electric circuits which protects the circuit and appliances from damage due to overloading and short circuit scenarios. It is a wire having a high resistance and a very low melting point. In case we have an excess current flowing through the circuit, which is the case when we have a short circuit, the fuse wire will melt and break the circuit. Fuse wire is made of a metal of an alloy such as lead, tin, aluminium and copper. Fuse wire is connected in series with a live wire. Now what happens when we have an overloading? Overloading is caused due to increase in voltage, or if there is a live wire and neutral wire connection, or if too many appliances are connected on a single socket. This results in overheating of wires and may cause damage to the circuit and the appliances. Short circuit. Short circuit is caused when the live wire and neutral wire come in contact and then the current suddenly increases in the circuit. It causes a spark, fire and a damage to the circuit and the appliances.